Thanks for the honor, the participation prize of this conference. Great. Okay, so thank you everyone for still being here. Thank you to the conference organizers for inviting me here. And thank you to the weather in Santa Barbara for making me feel like I never left England in the first place. Okay, so I gave a rather vague title for my talk. That's mostly because I didn't quite decide what I wanted to talk about, so I'm going to make a somewhat tortured connection between the two halves of my talk. But ultimately, what it's going to connect to is something to do with this, which is a visualization that in some form or the other, many of you will have seen over the course of this weekend, over the course of your lifetimes. So this is a visualization from the Aquarius project showing the growth of the halo of a galaxy like the Milky Way. And what you see, of course, is that the big dark matter halo, in the very center of which will be the galaxy, is surrounded by a sea of tiny lumps, and the sort of growth history of this object is characterized by many, many mergers of these lumps over the course of time, some of which might have galaxies of their own, some of which may remain dark. Okay, and as a couple of days ago gave a very nice introduction as to what happens when these sort of star-carrying lumps actually fall into the Milky Way, eventually disrupting and creating these features called stellar halos, which can in some ways be thought of as a sort of archaeological record of the merger history of galaxies like the Milky Way, and so is a very powerful tool because this is a clear prediction of what hierarchical models of structure formation would predict. So that was obviously relevant to the more massive galaxies, and the question I want to explore in the beginning today is what happens in the regime of dwarf galaxies. So is this picture of the stellar halos still something that persists in the lower mass scale? And after 4 days of this conference, I need not to introduce to you why the dwarf galaxies are interesting in their own right, because we know that if there is a cutoff in the primordial power spectrum of the range of a few keV, so it is in the regime of the dwarf galaxies that these features will manifest. And of course, if the stellar halos are constructions of even smaller mergers onto things that are already themselves small, then we get closer and closer to the regime where dark matter models really start to deviate from one another. Okay, so this question of what happens when satellites or smaller objects fall into dwarf galaxies or objects of different masses is not something especially new. So this is showing here, for instance, some work by Purcell and collaborators from 2007. And so what this basically shows is essentially for different panels, each panel shows a different host mass. So Milky Way-like masses here, clusters here, and so on. It shows what is essentially the amount of stellar material that is present as a result of accretion of other smaller objects, and whether that stellar material is in the form of galaxies that still survive, so the mass of the satellite is on the x-axis here, or whether it's in the form of disrupted galaxies, okay, in the sort of cyan lines. And one of the interesting things that you notice is that if you go from the larger masses, the larger hosts to the smaller hosts, as you decrease this mass scale, the dominance of these destroyed objects becomes greater as a function, as a fraction of the overall material. And so these, in principle, could be the kinds of things that are contributing stellar halos themselves. And so I think one of the things that is really interesting about this is the fact that this no longer is just a theoretical prediction, but is increasingly becoming something that might be a reality in observations as well, that we might be detecting stellar halos of dwarf galaxies. So this is some work by Anirudh Shetty and collaborators who looked at the Tucana 2 galaxy. And so what they find is, member stars of this galaxy that are confirmed by radial velocities projected in this plane here. And then if you construct essentially the profile of the metallicities of these stars, you notice that there are, some of these individual members that are associated with this galaxy that are located several half-light radii away from the center. Okay, and the claim in the paper is that if you were to look at the orbit of this galaxy, it doesn't really seem like something that is caused by tidal disruption. And so this in itself could be an example of an extended stellar profile or a stellar halo in a dwarf galaxy. Right? So to see what cold dark matter might predict in this regime, this is a calculation that Alice Deason and I and several others in Durham did a few years ago. So we started with an n-body simulation, which allows us to basically compute the census of mergers that are experienced by objects of any given final day mass. So this is a 10 to the 10 solar mass object. The white curves are what we want to focus on. The solid curve is showing major mergers defined by some ratio of some range of mass ratios. The dust curves are minor mergers. Okay, and so one of the first things you see is that by present day, something of the order of 10 to the 10 by mass today has experienced roughly around 7 minor mergers, at least defined this way, and of the order of 1 or 2 major mergers, roughly defined this way. Bless you. And so of course this doesn't tell us about the stellar material in this, and this is a dark matter only simulation. So what we have to do is to get a sense of what stars might be contributed to this. We need to know 2 more things, which is what fraction of these objects might contain a galaxy. So this galaxy halo occupancy, which is shown here. And once there is a galaxy, how much stellar mass do we expect that host to actually have? And so we were pretty general in this situation here. We didn't really assume any specific model, so we chose 2 bracketing cases. One case, in the case of halo occupations, where we chose something called the high threshold model, where only relatively more massive objects are able to host a galaxy of the order of 10 to the 9 or so, and one sort of lower occupancy, low threshold model, where more smaller objects are able to contain a galaxy. There's a little bit of debate in the literature as to where exactly this threshold is. And again, in terms of the stellar to halo mass relation, we heard from Stacy that there's a lot of uncertainty in this regime as well. So we considered a model where there's a shallow slope with a constant scatter and a steeper slope with a growing scatter towards lower masses. So what we can then do is for each of these scenarios work out the number of stellar mergers that these dwarf galaxies experience at present time. And so what you notice is that there's quite a big difference between what happens depending on whether you are in this high threshold regime or the low threshold regime, so where you think the minimum mass scale for galaxy formation is. And the key takeaway to all of this is that you can actually get really large differences in terms of what you think the number of stellar mergers are that these dwarf galaxies experience, depending on what you think the galaxy-halo connection is in the regime of dwarf galaxies. So there's a factor of 16 that is different here in terms of at least, say, the number of minor mergers experienced by these objects depending on which threshold you choose. And in fact, these differences can, in many cases, overwhelm the differences that you actually get between different models of dark matter alone, which is why this is a critical thing to keep in mind. So where does this stellar material actually end up? So we did very simple calculations of just idealized halos smashing into one another and then tagging certain subsets of the particles with stars, and then seeing, once you assume these different kinds of models, where does the stellar material get thrown off to, and how much of it exists in the form of these nebulous material on the outskirts. So this is basically showing, as a function of the dark matter mass ratio, what is the fraction of stars that is located about 10% of R200 and greater. And going from left to right, we go from a shallower to a steeper slope in the stellar to halo mass relation. And essentially, you find that there is clearly a difference here. And one of the most interesting things is that the merger ratios, or the objects that are actually bringing in these stellar materials, what they are really matters in terms of whether or not we have substantial amounts of luminous material in the outskirts. And in particular, if you have mostly major mergers or mostly minor mergers, you have very little amounts of stars in the outskirts due to basically dynamical friction or basically not bringing in enough stars in the first place. So there ends up being this sort of sweet spot of around intermediate mass scale mergers where this richness of the outer halo is kind of maximized. So in some sense, if we find these stellar halos in dwarf galaxies, it is roughly at this scale that the sort of efficiency of detecting them is maximized. It kind of just works out as a balance between binding energy arguments and whether you bring in enough stars in the first place or not. So what about the detectability? So one way you do this is by actually predicting what we call a surface brightness profile. So it's just basically the amount of stars per square kiloparsec, and then you change that to arc seconds if it's at some distance and so on. And basically what's shown in each of these panels is going from top to bottom, whether we go from a low threshold of galaxy, or high threshold of galaxy formation to a low threshold of galaxy formation, or whether you go from a shallow stellar to halo mass relation to a steeper stellar to halo mass relation. And one of the things you find is that if you have a very high threshold, or a relatively high threshold for galaxy formation, so only more massive objects carry stars in them in the first place, you get somewhat more compact profiles, because these are larger halos in general that have the material, and so these halos, when they merge, they basically sink to the middle and don't create extended material on the outskirts. Whereas if you have a lower threshold for galaxy formation, so many more smaller minor mergers are able to contribute to the luminous stellar halo material, you can start creating these shells on the outskirts. So this gray band going horizontally is basically what we think is the sort of detection threshold for something like the LSST. And you notice that for any one particular galaxy, the solid white curves are the average profiles. You don't necessarily observe anything, but when you start stacking objects, 10, 50, or 100 objects, you might actually start detecting these stellar halos. And so the main point here is that the very existence of these, if they are detected, might tell you something very fundamental about the stellar to halo mass relation in the regime of dwarf galaxies. I just want to quickly flash a sort of ongoing work by a former student at Durham who's a postdoc in Sweden now, Tilly Evans, who's now looking at the statistics as you compare them between warm dark matter and cold dark matter, in this case a sort of 7 keV stereo neutrino. And essentially you find that there are these differences in the merger statistics, not only for the lower mass regime, but this actually propagates to relatively more massive objects as well. And there are differences also in terms of the environments that these things live in. So actually you can expect to see a diversity of these profiles as you change between dark matter model and as you change the environments you live in. I also wanted to flash out one more thing, which is that in our simulations, which are pretty high resolution, so a 10 to the 10 solar mass halo is resolved with 100,000 particles in this case, we have actually produced a full catalog of stellar halos under assumptions of different galaxy formation physics, 2 different kinds of dark matter models, and over 3 decades of halo mass. And in the spirit of what we were talking about yesterday afternoon, we are planning to make all of this data public. So if you are interested in doing galactic archaeology for Milky Way mass scales or dwarf galaxy mass scales, then this is something that could be useful to you. I should say, just finally, that the detection of these dwarf stellar halos beyond what I showed earlier is also becoming a reality now thanks to JWST. I just want to quickly show a result from Charlie Conroy's group from last year, looking at the ARC 227 galaxy, which is about 10 to the 9 solar masses in stellar mass, where they observe these kind of shells in the surface brightness profile, thanks to the resolved stars that you can now get with JWST. And these features really are reminiscent of some of the minor merger-based scenarios that I was showing you earlier on. So I think it's a really interesting time to consider these objects in detail. Okay, so here's the really tortured connection to the next part of my talk. So I talked about merger statistics and how the differences in mergers can tell you potentially something about how galaxies grow and what different dark matter models do. And these differences are especially pronounced at high redshift. And so one way you might think you might be able to study what happens in terms of the growth of objects at high redshift is to make use of new frontiers of observation. And in particular, we considered the case of whether or not gravitational wave backgrounds through binary black hole mergers can ever tell us something about the nature of dark matter. So this is an interesting question because over the course of the next few decades, we'll have a really great new set of facilities, hopefully, if they come to fruition, that will enable us to characterize the statistics of these compact mergers going up to the very earliest phases of time, and in particular making us sensitive to the very high redshift universe, which is indeed where models of dark matter appear at their most discrepant. So I wanted to show you very quickly a very simple exercise that we did with some collaborators in Australia and Denmark. This was work led by Marcus Melsbeck, who is now a postdoc at Aachen University in Denmark. And so in particular, we considered the case of cold dark matter, as one does, but also an alternative dark matter, which in this case is something called interacting dark matter, where the dark matter particle basically has interactions with neutrinos in the early universe. And what that does is that it leads to this sort of collisional damping on small scales, leading to oscillatory features on the small scale power spectrum, kind of like the dark acoustic oscillations we've seen previously. The net effect is that depending on what the interaction strength is between these two species, you can get very strong deviations from CDM. So this is showing the abundance of dark matter halos as a function of their mass and their suppression relative to CDM for different choices of this interaction strength. And you can dial this number back and forth, basically. And to get a prediction of the gravitational wave background, we went through a series of steps. So what we first do is we generate the linear power spectrum, which I think we guessed we kind of understand to do well. From that, you can run simulations that are full n-body simulations using the gadget code with a special modified version of it. And then, instead of using the simulations directly, because the simulations are limited by resolution and volume, what we do is we actually use the outcomes of the simulations to calibrate a Monte Carlo version of generating halo growth histories through a variation of the extended pressure approach, which is calibrated so as to reproduce what the numerical simulations give us. That allows us to essentially get very, very high resolution merge trees, but also over very large statistical samples in a way that the simulations alone would be very difficult to do. On top of these merger trees, we then create synthetic galaxy populations using a semi-analytic model of galaxy formation that we call GalForm, which has all the bells and whistles that you would think would be necessary for the galaxy formation process, including cooling and star formation and feedback and black holes and stellar population evolution and so on. That allows you to predict galaxy populations. And then finally, what we do is we use a binary evolution code called COMPASS, which has been used quite significantly in various gravitational wave papers and so on, to essentially take the individual star formation histories and metallicity histories of galaxies predicted in each of these models, and then therefore predict what the binary evolution would be in these cases. Okay, so how do we actually determine what is the appropriate set of galaxy formation parameters to choose? So one of the things we do is that we try and reproduce as best as we can what the present day data looks like in a few statistics, because we want to try and see that we can actually not just predict the high redshift universe, but actually predict observations that look vaguely realistic at present day. So this is something called the B-band luminosity function. So it's a number of galaxies as a function of their brightness in a particular filter. Bright galaxies on the right, faint galaxies on the left, observational data shown in the symbols, and the different models shown here. So lambda CDM and these two low interaction strength models in cyan and yellow match these data very well. And you see that there's three different versions of this pink curve, none of which really match the data very well. In fact, the version which is in this dashed dotted line is a case where we have completely turned off the effect of feedback, basically allowing every dark matter halo that could form a galaxy to form a galaxy, and yet you can never reproduce the data simply because there's too few dark matter halos to be able to match these observations. So this is actually a very strong test, saying that no matter what you do, you have no degeneracy with astrophysics here, because basically there's not enough halos in the first place to give you a reasonable galaxy population. But once you've done that, you can start making predictions about the binary black hole merger rates. So this is what the CDM case looks like as a function of redshift. The pink shaded region is basically the current constraints from LIGO, Virgo, Cagra. And then as we put all the other models in there, you see that there's this generic feature where they all look very different at high redshift, and they all kind of start collapsing onto a singular region at low redshift. And this is a very generic prediction of models where there is a free streaming or there's a cutoff at high K modes, where there's differences at high redshift that then basically start getting washed out as you get to lower redshift. Okay? And so would you ever be able to detect these differences? This is the last thing I want to show. We made basically a prediction of the number of objects or number of these events we expect to observe given some particular observation strategy. That is basically a function of the observing time, what we think the merge rate density is, the population distribution, various parameters, and various probabilities for observing. This is what CDM looks like. We put the other models in. It turns out that for the really extreme models, up to this 10 to the minus 7 interaction case, you can potentially distinguish these with pretty good statistical significance. But when you get to these lower interaction strengths and things become very much CDM-like in terms of their mass functions, actually it can be very hard to actually distinguish the effects, at least in terms of binary merger events. So this is my summary. So the census of galaxy and halo mergers across cosmic time is sensitive to the dark matter model and the environments in which galaxies grow and evolve. And interestingly, some of these differences propagate even up to the more massive galaxies, so we need not limit ourselves just to objects near the free streaming scale, depending on what kind of observations we're interested in. So low surface brightness and diffuse stellar features in dwarfs can be important as probes of dark matter, but probably also more importantly, what the galaxy-halo connection is in the regime of dwarf galaxies. And I think there's interesting and exciting prospects that are offered by future observatories, but I think there's still a lot of a nascency to the way we model things that need to be improved on. So these are things I'm really interested in exploring as time goes by. So thank you very much for your attention.